Hi. So recently there's been a lot of talk about clean code and optimization going on Twitter. And a few people asked me if I could uh, do this presentation again. I did it at a private conference, so not a lot of people have seen it. And yeah, the basic idea is to talk a bit about practical optimization of code. And what this talk isn't about is the normal sort of optimization stuff you see. A lot of talks I see about optimization, they're about looking at the assembly, SIMD instructions, reordering or refactoring math and using intrinsics and how the compiler is going to compile your code, or what the chip architecture is and how to write for that architecture. And then if you get into sort of data-oriented design talks, it's a lot about structure alignment and caches, and this. Even though I'm going to be talking in the context of Unity for a lot of this, it really does apply to any game engine, to any program, and it's not about squeezing this 10% gain out of an inner loop routine. What this talk is really about is that none of this really matters until you do this one crazy trick, and with this, you can get 90% of the gain for about 10% of the work. And what I'm going to do here is walk you through some synthetic examples, but then actually show how those apply in real world examples of code I've worked on. And hopefully what this will do is distill it down to some simple advice and approaches and some awareness of some things that you should look for when you're writing code. And essentially what it all really boils down to is how you access memory and its access patterns. So there's been a big movement over the last few years about data-oriented design. I'm a big fan of this stuff. It can be taken too far, like anything, but understanding it is very, very useful. And the essential sort of summary of this is that coding in schools is taught wrong. We're taught object-orientism and structures which really work against code being fast. And that memory is really slow to access. Computation is actually fast, that you can compute hundreds of things in the time it takes to fetch a piece of memory that's not in the cache. And the basic thing you want to do is always access memory in linear order, and don't load what you don't need, which is very easy to do, and write for processing many things, not just one thing at a time. And from this, you get that array is your one and only data structure. And you'll find yourself favoring arrays over other data structures when in a more traditional approach would say to use something more complex. So one of the best examples I heard of this, I heard many, many years ago. I think it was somebody from id who said it, who said, don't write a rocket class, write a rocket manager. And so if you think about like a rocket, this is a simplified example, but it would have some position and velocity, and you'd have some update loop that comes along and says, great, let's add our velocity to our position multiplied by however long it's been, and that will move the rocket forward. But in practice, if you want lots of rockets in your game, you're doing a bullet hell shooter or something like that, you really don't want to do stuff that way. What you really want to do is treat everything like a particle system. And so in this case, we have a rocket manager. It has a list or vector of positions and another array of velocities. And depending on what language you're in, this could be any sort of continuous memory structure. In this case, I've coded it where I know I'm never going to have more than 1,000 of them, and I'm using C# arrays. You could do this with a C# list, so you can extend the length of it and stuff. It would cost you a little bit of performance, but if you want to sort of know less about your data, that can be worth it. And then the main thing here is that when we actually do that update loop, we're just going through this local list. Instead of every rocket in the game updating themselves, we're just blasting through this nice continuous memory of the positions and velocities, and we are adding that. It's supposed to be times time. I forgot to add that in there. So yeah, that's the basic difference that we're talking about. It's not a huge change, and again, there's multiple ways you could do this. So let's take an actual example, and I'm going to profile it. This is a synthetic example. We'll get into some real ones in a minute. But this is a monster class, and in this, what we have is we have a monster has health and stamina, and if they have health, or in this case stamina, then and it's less than the max stamina, they're going to regenerate some of that health and stamina. And so object orientism might say, hey, don't write this out like this. Let's just have a regen stat class, and you could do that, and then maybe you refactor that into something where it gets more and more complex. But your problems are just going to grow more and more as you do that. And so in this, we have an update loop. So this thing is going to update itself every frame. Unity calls an update on any object that has that function. And we're just going to increment health and stamina if we have to, and make sure it doesn't get greater than the max amount. Pretty simple, pretty straightforward. You see this type of Unity code all the time. So the first problem when I look at code like this is you're kind of unsure of what's mutable and what isn't. I like stats and things to be in their own place because I know they're not going to change versus, or rather the parameters of kind of like max health and regenerate. And then I want the actual mutable state that's changing all the time to be the only thing I'm working with on every one of these objects. And so we've got configuration state and mutable state kind of mixed up here. And then of course we have Unity's. We're using Unity's framework for updating. And so to time this, I just said, great, let's have 200,000 of these and run it, and what you get is 27 milliseconds of processing time to do this on 200,000. Now, in most games, you're not going to have 200,000, monsters, but it's a useful thing to see the timings. So let's just change this a little bit. Let's get out of the Unity framework because anytime you have a program has a framework, it almost is always going to have some kind of overhead cost for that framework. And so instead of actually just having every monster handle its own poll, we can just basically make a monster class and give it a poll function, and then we can have a monster manager that's just going to go through that list of the monster classes and essentially call poll on them. And just doing that takes us down to 6 milliseconds, which is 4.5 times faster for not having the framework overhead of the update loop. So what this really points to is, if you have some framework that's doing things like handling polling and things for that, you might want to try just owning your data and calling your own functions on it instead of using that framework. In this case, we're using it to get called once instead of 200,000 times, and it makes us 4.5 times faster. So let's fix up that memory layout a little bit, and instead of actually having that be a separate component that's sitting on an object somewhere, we're just going to make a structure instead. And we're going to leave the exact same stuff in it. So we haven't changed really anything. We've just changed the class from a class to a struct and made it not a mono behavior sitting on some object somewhere. And so we need to be able to access that. So instead, now what we have is an array of monster datas that's 200,000 long. And we'll see this takes us down, gets us about 3.5 times faster just doing that. And so we're at 1.7 milliseconds now from 27 milliseconds. Okay, and the code, if you'll notice, the only real difference here is that we have a struct instead of a class, and that we are allocating all of that in a nice linear array of those structures. And we have a manager class that's just calling update on them instead. So we really haven't introduced new code complexity or even that many lines of code, and yet we're already 16 times faster. So why is this? Well, it has to do with the way a CPU attempts to read memory. When you say, hey, go get me this memory, it will assume that you need the memory right after it. It also will go ahead and grab certain chunk sizes. So when you are grabbing a list of classes, what it's kind of like, you can think of it as like if you went to Hollywood and you got the map of the stars, and then you drove to one star's house and then drove to the other star's house, right? They might be scattered all over town. You don't, you get in the car, you look at the map, you decide which one you're going to drive to, and then you spend 20 minutes driving over there in LA traffic, right? That's kind of like the class model here. But when you have an array of struct or an array of any data, the CPU, instead of getting the list of where everyone lives, it's actually getting the actual data instead. And so it's kind of like if you had all the stars lined up in row houses and could just walk from one door to the other, right? So much, much faster. You're not dealing with LA traffic in 20 minutes of, or 2 hours or whatever it turns out to be. So that's kind of the difference between having classes spread out all over the place and then having data which is localized in an array. It's much, much faster to traverse. So where we are right now, we're about 16 times faster. I would argue that this code is easier to maintain and deal with because it owns and knows about the data it's working with. There's not a thing of like, well, how many monsters do I have in the game right now? They're all centralized. I don't have to find all T functions that, who knows what they do, what they cost, troll the whole scene and find all these things. I do have to do some of my own bookkeeping when adding and removing, but it's all fairly straightforward stuff. And what this actually does is open us up to even more possibilities for optimization. And so let's go there. Unity has a thing called jobs with a system called burst for compiling the code faster, and Unreal has a system like this called mass, and most modern game engines are going to have some kind of job system at this point. So whatever you're working in, and whether you're working in raw C or C# code in an application, you probably have some way to thread code. And the thing with threading code is that if you have these really complex tangled data structures, it's much harder to gather all that data and move it over to another core. And so when you have everything in these nice array of structs or structures of arrays, just plain old data that you can zip through and it's, all in one spot, it's very easy to thread it. So in Unity's case, we switch this to what's called a native array, which is just what their job system uses. And we get rid of that update from the structure, and so we just have the structure itself. And then what we have is this iJob parallel 4, which basically I'm going to run on 1,000 of these entities at a time in each job. And so if we have 200,000 of them, we're going to make 200 jobs, and we're going to wait for them to complete. Now, in a real case, I could continue doing more stuff on the main thread while this was going on. So a lot of times, this actual cost we're at now is going to get completely masked by the fact that we're still able to do other stuff. And in this case, this takes the 200,000 entities down to 0.25 milliseconds from our original 27 milliseconds, right? So we're orders of magnitude faster at this point. The code does look a little bit different at this point. You have to understand the job system a little bit. But it's really like the actual function here is just our execute function is the equivalent of our update, and that we're using this different array type, and that we have to pass in delta time so it knows time. And then we kind of launch this job and force it to complete right away in this case. But normally we would wait for that to complete and do other things while we're doing that. So that's just taking the exact thing that we have and converting it over to a threaded system with the Burst compiler, which also helps. Burst knows a lot about the data structures and can write more optimal C++ code from your C# code. That's a very Unity-specific thing. Originally I talked about this configuration state versus immutable state. So let's actually make a design change here. In our original version, all 200,000 monsters could have different regeneration states, different max health. I suspect that in most cases this isn't really useful, and that you're going to have all whatever the monster type is has the same basic config stats. So let's pretend that that's the case and just see what it does to our code. And so now we don't really need a monster data class. We can just have a native array of floats for health and one for stamina. And we can set that config state on the job so it knows, here's the max health and stuff, and we don't have to store that and access and load that memory for everything that's going on. We only need to access that one float per thing. So what that does is means we can get a lot more back from the cache. And we'll see that this just about doubles the speed of these operations again, and we get down to 0.13 milliseconds, which is really fast, right? So all we've done here really is we've organized our memory in a way that we know how it's allocated and control it. And we've removed some framework overhead by just doing the polling ourselves. And just that gave us a 16x speed up. But because that made it so easy to jobify now, we ended up with 108 times speed up without changing the design at all, and a 216 times speed up if we have that one little design change and decide that we don't want every monster to have its own max health and regeneration rate. So so let's take those ideas and apply them to real world code. Okay, and I'm going to be less in the code and more top level in this, but I think it'll give you a good idea. So I worked on Kerbal Space Program 2, and they had a planet rendering system. It's based on a reasonably common technique called a quad sphere renderer. And the basic idea is, like, if you have a planet and you've got to be able to go all the way down to the ground, and then you need to be able to come out all into space, you need to be able to handle levels of detail so that you're not suffering from tiny little triangles and millions of triangles. And when I got this, I don't know what state it is. There's a great talk on Kerbal 1 and how they built the planet renderer for that game. It may have gone through some changes since then, but this was the code as it was dropped to me. And what I've noticed right away was these large hitches when you were crossing detail boundaries, and it would have to recompute. And these would get worse if you were flying really fast, right? And it had to compute more levels of detail. And they were generating, basically for each of these little quads, they were generating a game object and a mesh for it. And then the way they had structured it was kind of in the Unity way, where you have a component on every game object that has its state on it, much like the monster data was originally in my example. And it would tessellate up to about, I think it was about 16 meters per triangle at its highest resolution, and they wanted to get a lot higher than that. And had ideas for features and all kinds of stuff. And the way that this was optimized was by breaking the work up over frames. So if you suddenly teleported to the other side of the planet, what would happen is that you'd see this up-resing where it's low res, and then it would get a little higher and a little higher and a little higher. So you'd see like 13 or 14 frames of it constructing the planet. And that was kind of how they had optimized it. I don't consider that optimization because it's just spreading the work around, okay? So the basic algorithm for quad sphere renderer is pretty simple. You figure out the desired detail level you need for each quad based on where the camera is, and then if you need it higher, then you split that quad into 4 of them, and if it's lower, it's just replace 4 of them with 1 of them. And there's some stuff about edges, but it's not important here. And in this case, because of the amortization, they basically never computed more than 1 level change at a time, but they also, you never jump more than 1 detail level in a distance, so you get this kind of gradual fade out of the quads. And then essentially what this code did, and again, this may have been modified from the first one, is that it would go through each vertex in the mesh, and then it would pass it to a processor, or a list of processors essentially, and they would modify that vert. And so you could have like height map lookup and noise and all kinds of stuff. And first of all, just inverting the way this works would have been a massive savings. And so, whoever wrote this code really didn't understand that calling virtual functions has a significant cost, and just reversing this would maybe prevent the ear of Mike Acton's side eye here. So what you really want to do, if you were really going to do it this way, is you want to grab the list of verts and then have each process the whole list, because that's going to be a nice array in linear memory instead of calling a virtual function for every single vertex, right? I think the vertex count on a quad was a couple hundred vertices, and so that just knocks out hundreds of virtual function calls right there. What I did to fix this is, first of all, I removed a bunch of the amortization, right? I got rid of all of those optimizations so I could really see what I was dealing with. And I removed the limit that it could only adjust. I wanted it to adjust all on the frame to what it needed to be without sort of this gradual up-resing, right? And what I got on sort of not even a really stress case, but like a general moving around, was about 1,800 milliseconds per frame when it crossed a boundary and had to adjust the detail levels, which is really, really slow. The first thing I did was fix the data structures. And again, this is exactly what we did in the monster example. So I got rid of the components on every game object. I still had game objects to hold the meshes and get rendered at this point. But I moved all the data into the mutable parts of the data anyway, into a structure that was just allocated at a max number of quads in a nice linear array. It might have been a class instead of a structure. I'm not going to get into the difference there and why sometimes one is fine and not the other. But I basically took it off all the components and made sure I had it in nice linear memory to access. And and I'd still create the game object mesh for now. And then I took out that vertex processing virtual function. It turned out the artists were just interested in using a bunch of height map operators on a ton of very high-res height maps. And so I just wrote that as a single function that would get called, and it would get past a list of vertices and run that function. And so at this point, I haven't threaded it or anything like that. It's 300 milliseconds. It's already significantly faster than it was just by changing a little bit of data. And this is really only when crossing, and it's like not the worst case at this point, because once you're up in a 2-second delay, it's not worth worrying about whether you're in the worst case anymore. Your case is terrible. And so on the second pass of this, we wanted to make it faster, but we also wanted to up the detail level. And I think on this stage, it was about 2 meters per triangle, so significantly higher res. And I moved the mesh construction to jobs burst so that we could do it all in parallel. And the worst case in this, when this was done, ended up being around 10 to 30 milliseconds. And so, at this point in a normal game session, it's actually fine, but there's so much stuff going on in a large game that taking up 10 milliseconds even seems like it's a lot, because you still have to render, you still have to do physics and all the other stuff going on. So I definitely wanted to get that down lower. And so kind of in a third pass, what we did is I took the LOD calculations, I made them all into jobs burst so that they could be done in parallel, which saved some time. And then I moved all that geometry construction to Compute Shader. Actually, that was a coworker of mine who did a lot of that work. But once you have things in jobs and bursts, it's really not that hard to move them to a Compute Shader. And we increased the detail level some more, and we added a decal system so that you could stamp on local geometry and move it around, which is very useful. And at this point, the construction of the actual geometry is stateless from frame to frame. We're not reusing geometry each frame. We're actually fully constructing the geometry every frame from scratch, right? We're not generating the new pieces we need and trying to use the old one. We're just generate it all every frame, and there can be no caching errors or bugs from the fact that it's using the wrong piece or whatever. It just goes from the beginning. And what this does is Now it's taking about half a millisecond on the CPU and about a millisecond on the GPU to do all the work. And by the way, this was on essentially when I was doing these timings, it was on a MacBook essentially. Excuse me one second, my alarm keeps going off. So we're at a point now where the detail levels are probably, I think, 16 times higher. We're not getting this kind of janky, up-resing of the world and popping stuff going on. We've got more features in the system. It does exactly what the artists need, and we've still seen it's 1,800 times faster than the old system was in its worst case scenario, and it's about half the code of the old case, so much easier to maintain with less code. The code is simple. We know where the data is. It's not scattered all over the place. It's not a bunch of virtual function calls that you have to go figure out what actually they do on random objects. It's a very simple to read system. And why we did that, we also, or actually Leonard did this, he compacted all the mesh, the little meshes into one mesh. So now we just get a single draw call for the whole planet. And we don't have this giant game object transform hierarchy for all those render objects and stuff because we're just drawing one mesh. And so just want to reiterate that this was basically the same stuff that we did for the monster example, except we moved some stuff to compute to be done on the GPU. And there's a lot more details in all of this stuff. I mean, I'm just trying to get the point across about just fixing your data structures and understanding the code that you write and what it's really doing, right? So I worked on a game called March to War. I did a whole presentation at Unite in 2017. You can just search for Walking Dead Unite 2017 to find it. Earl's there. That talk is like a ton of like low-end optimization tricks and kind of old coder hacks from older times, because we had to get this to work on a low-end mobile device, which was an OpenGL 2.0 device at the time. And so this was a thing where we had massive cities built out of lots of little parts. It was a streaming world. We wanted full post-processing running even on the low-end mobile phones that we were working on, and it shipped in Unity 5.6. And to do this, we ended up building a lot of our own systems for things. Like we had this randomizing prefab system that was nested, and we used this basically to generate all our levels and then stored in a custom format. And so if we just saved our data in the scene format, it turned out to be 41 megabytes for one of those blocks. The blocks I'm talking about are these blocks. We had a ton of these in game. I think there was a grid of 64 by 32 of them. So 41 megs times that many blocks, it's a lot of data. 41K, that's way better. So a prefab for some reason was half the size of the scene. I'm not sure exactly why. I didn't bother to look, but we wrote our own serialization model. And essentially we called it a pack transform, and it was 64 bits in total, basically because we didn't need all the rotational axes. We didn't need all the nonlinear scale and stuff. So we basically just packed that down into the precision level that we needed and stored it as this object is drawn in all these positions, which just happens to be how you want to draw things on a graphics card anyway. So that all kinds of works out and massive reduces download size for streaming. But we did this kind of packing with everything. The navigation map for the AI. So we needed AI groups to basically not only A-star their way to places through these structures, but have local avoidance of both the objects that were in the level and also of each other. So because we pack this down into essentially a bit field at a low resolution, it ends up being half a K. And so when you're writing code that needs to do lots of memory operations like raycasting through something, if that memory is all packed really tight, then it doesn't need to go and grab more of that data from some cached memory in some cache somewhere or from disk, So 0.5 kilobytes, half a K, will fit in the cache on pretty much anything. And so all that data, once it's there and doing its lookups, like the lookups become really, really cheap because it's just right there. As soon as the processor has to get memory that's not in its immediate cache, it's much, much slower. And there's like different levels of memory, and they get slower and slower. The slowest being the network, right? And then the disk, then the RAM, then these little caches that different processors have different arrangements of. So just squeezing that data down makes the code run faster. And I did this on everything. So this is a height map we use to do camera avoidance, and we build a nice spline path. And you might think, well, okay, doing a nice spline path over everything must be computationally expensive. I mean, not really, because as long as I can fetch the memory for the data I need, it's really, really quick. And so, again, computation is fast, fetching memory is slow. And so by packing these things down into the smallest memory possible, we're pretty much guaranteed that things will run fast, even on a really low-end mobile device. Another example, player bases. And then, because all this data around our game is being packed so tightly, we can afford to do more with it. And so for fun, we wanted birds in the level, and I do a whole flocking system for the birds flying through the level, and they fly through that height mass that I had earlier. So they're flying through this kind of low-res version of the level up high. And then because we can pack these transforms down really small, and when we just need a position, we're just using 3 shorts, essentially. So we had all these bird landing spots, which is what you see here, these little yellow balls on things. They wouldn't render to the user, but that's how we place them. And we just placed them in the prefabs, and they just showed up all over the level. And then birds could seek for one of those spots and land on it, because, again, all the data they're working with is tiny. So if you go through a list of birds to update their positions, and then they go through this little bit mask here to figure out where they can fly, and et cetera, then it all just goes really fast. And, again, I'm not even... I did some classical optimizations here, like not using Unity's math library and writing my own, because the old math library in Unity was really, really bad. The new one's fine. It's pretty good. So, there were some classical optimizations, but for the most part, it's really about memory and how you access it. So to summarize, packing your data down for your systems like this, it not only makes it easier to stream to users, makes your app smaller, makes you take less memory and stuff like that, but really it's about making it fast to work with. And writing custom systems that only do what you need, right, can massively help your performance. And you can write simple code because it only has to do what it needs, not some future thing that it might need one day. All of that kind of stuff is slow. And so this is how you get massive numbers of zombies and birds and buildings. And we were drawing 10,000 objects on a frame because it was all simple and customized and used small data. So I do a lot of assets for the asset store. If you're on this channel, you probably already know that. But one of them is Microsplat. It's a terrain shader. And terrain shaders can be very expensive. And there's all kinds of tricks that different engines use to get around this expense. Now, Unity's terrain system is pretty old. I think they coded it in 1871 or 1897. Yeah, it was around the before the Model T had come out. It's a very basic terrain system, and so when I looked at other shaders and why they were so slow, because somebody had asked me to do that, I realized they're all a natural extension of the Unity shader. And so the way the Unity shader works is that if you have 16 textures on a terrain, or what it'll do is it'll sample 4 control maps, which are basically just weight maps with RGBA mapping to how much each texture is used. So if you have 16 textures, you have 4 control maps. And then it would sample all those textures, all 16 of them, and then their albedo, their normal, their mask map, whatever actual textures they were. And after it does all that, it blends it all together. And so if you just add like triplanar texturing to that, and you do the brute force thing, you're going to end up with 148 samples because triplanar has to sample from the side, the top, and the front, right? And another common technique is distance resampling, which is just resampling everything at a certain distance with a different UV scale so that you can still see the rock details and it doesn't just turn to a color. That doubles the number of samples. And so if you have those two features on, you're looking at 292 texture samples per pixel, which is a brutal amount of memory lookup. So stepping back on this, if you really look at a terrain, most of the time, most of the areas of the terrain are only using like 1 to 3 textures, if it's blending between areas or something, but it's like generally it's like grass or grass with some dirt in it, stuff like that. And so why are we sampling all 16 of these, right? So the first optimization was just let's just stop doing that. Let's just pick a number. And so what I do is I get the weights from those backing textures. I sort them so I know which ones are the most important. And I just get rid of the other ones. I just say there's 4 weights I'm going to sample because quite frankly, you can't see more than 4 anyway. And especially if you're doing height blending and things like that where one texture tends to dominate. So I'm just going to only sample 4 of these texture sets ever. And so what that does, if we compare, is a traditional technique with triplanar and distance resampling on is 288 samples, and mine would be 52. So we see a massive savings in memory bandwidth from just kind of looking at our scene, reasoning about it, and figuring out how to not do wasted work, right? And so that leaves us space for more features that we can add. So not just more speed. Optimization is a feature. It's giving you the ability to have other features. So why stop there, though? There's other things we're not noticing here. And shaders can do dynamic flow control, which is basically branching if statements. And everything you read online is like, never do an if statement in shader. They are wrong. If statements are wonderful things. You just have to understand a little bit about them and how a GPU processes to understand how to do them. And I have a blog post on all of that. So first, what I'm going to do is just branch by the splat weight. If it turns out there's only one texture set being used because it's a big plane of grass, why am I sampling the other 3, right? Or the other 16 if I wasn't doing my first kind of cut pass. And then I just go down the feature stack. Okay, do I need all 3 triplanar angles? I have a thing called stochastic texture clustering that's technically, requires 3 samples of a texture and it kind of breaks up tiling. Maybe I can branch on that, or distance resampling. And so I just went through my various feature stacks and things and basically put that in, and I wrote visualization so I could see what was going on. And so if you have a render like this of a terrain, what you actually see is the darker areas are where we have less textures. So all the dark areas, we're basically only sampling 1 texture. And all the lighter areas are where we're sampling more of them. So if we call by this 4, we're all by this first, we're also culling all future things like triplanar and stuff. So that's like the first big savings. And if we look at triplanar, most of the time it's only going to be what's facing up, or it's going to be the 2 side textures. You'll notice that we see the 2 side textures all along here, but you'll see these little spots where it's lighter. That's where you actually needed all 3 textures. So you rarely ever need all 3 textures. And turns out stochastic is the same thing. In the blend area, you need more samples, and everywhere else you don't. And so by analyzing this, we can figure out kind of how we should set up our branching. It also means that higher contrast blends and things get you more speed because they cull better. And distance resampling, of course, you don't need it up close. So you cull all of that in the near field, which is where the textures are higher res, right? You're going to be sampling like the 2048 textures there instead of like the maps that are 64 by 64. So we actually save a ton by not doing it up close. And yeah, so if we go back and compare our brute force 16 texture terrain with In this case, it's going to be the basic texturing, triplanar, stochastic, and distance resampling, right? Which are all great features for making your terrain look good. It would be 864 samples plus 4 for the original control maps. That's an insane amount of samples. With the culling that I originally did and the dynamic branching, I visualized how many samples it actually takes. And you can see here, it's on that same scene, you're getting between 14 and 52 samples per pixel. So that's a 4x increase from from not having the dynamic branching, from just doing the cull down to 4. And I haven't timed it against doing it the brute force method at all, but radically faster to go to 52 samples per pixel from 864. So really, a big thing I want to point out here is that optimization is a design time thing. There's this sort of, wait till the end, wait till you see what needs the optimization. And I think that's true of algorithmic optimizations, of like moving things to SIMD or like getting really nitty gritty. But you can design your code in such a way that you can get massive speed ups without even like doing much in terms of just understanding, hey, don't put the virtual on the inside of the loop. Don't just go and randomly spew memory everywhere for things. Like, just keep it organized, keep your data organized, think top down about your data so your class knows what it's working with. And you'll see massive speed ups to your code. And that's not making your code less maintainable or uglier. It's just thinking about your data, right? And performance, when you get performance software as a feature, like, people are talking about how like a text editor is slow, which is ridiculous in this day and age, meanwhile, we're drawing these like massive worlds, and the only way we do that is by having performant code. And if we have performant code, that means we can add more features. We can have the little birds that land. We can have storms, hundreds of little zombies on our map that we couldn't have before, and all fit within the same budget we did before. So your games get better when you write performing code. And really, what I should be saying is that you want to write optimizable code, right? Like, if your data structures are terrible and it's just your processor is just sitting there waiting all the time for the data, and so it doesn't matter if you go in and make this routine a little faster or try to do something smart where it doesn't do it every frame. Like, none of that stuff matters until you fix your data structures. And once you do fix those data structures, it makes it really easy to thread things and do all kinds of wonderful things for performance. And you might not even need to do a lot of those things because you reach the point where you're like, well, you know what? I got so much other stuff to work on. I can make this 40 times faster, but we don't call it enough, so who cares, right? I just make sure my code is in a state that if I need to thread it, if I need to make it run fast, or I need to really get in with a profiler and like tweak every little thing of it, I can do that if I want, because it's in the right structure that those optimizations can actually count, instead of having to go back. Like, the process of taking a very large entrenched object-oriented system and fixing it is way slower than just writing the code the good way the first time. And you can write that the good way without having to like spend hours in the profiler or make your code ugly. I don't buy any of those arguments. You can still use virtual functions. You can still use like inheritance and interfaces and sort of object-oriented things to help structure your code. You just put them in the right space. You don't stick them in the inner loop. You realize you're paying a cost for that flexibility of adding the thing later that you might need. And there are places where that's perfectly acceptable. But whenever you're writing anything that might need to go fast, or you might not need to add to in the future, like, I think that the assumption that all code should be extensible as a first basis is harmful, because it sends us down this idea of making everything in a way that is incredibly slow, and just ends up with the text editing software that can't keep up with your typing. I mean, that's just absurd for the machines that we have today. So I want to tell one more story. Another optimization technique, which is probably the greatest of them all if you can do it. And I'm going to take you back to when I was working on Rock Band for the Wii and the PS2. Well, really, we were working on Rock Band for the next-gen consoles. And, I'd asked over and over, are we going to do this thing for PlayStation 2? We've got a lot of people with hardware. Like, we should consider it. And over, I was told, no. We're not. We're just next-gen console. And then our publisher came to us and basically had a chart of the mountain of money that we would make if we could ship by Christmas. And I think at this point, we were, maybe July. So the idea of taking a next-gen, or what was next-gen at the time, game and backporting it to the PlayStation 2 and to the Wii by Christmas was kind of insane. And so what happened is that we all got in a room and everybody was talking, and they were like, well, what if we cut out the character creator and we just had, 3 characters? What if we cut out the stages that we just had one stage? Okay. And I basically just said, why don't we, if we're going to cut all that stuff out, then why don't we just record the 360 version to video and put the live track over it? Because all of that stuff you're talking about cutting is all about customization, so that you can, customize your avatar and choose which background you're running in. And if we manage to, even with a reduced scope, get all that working, it's going to look far worse than the video. And they kind of looked at me like I had 3 heads for about a week, because they just thought, no, we can't get away with that. It'll never work. And then came back and realized it was the only way to make it work by Christmas. And so that's what we actually did. And, that made millions of dollars for the company by basically just considering a radically different option and figuring out how we could still deliver a compelling experience, but without the presumptions of how we had to do it. And I'm often amazed, I've been doing this for a long time, but I'm not the greatest coder. Like, people are always like, you're a shader wizard. I'm like, not the greatest at any of these things. What I tend to have is an overview of things that allows me to find different options to get what I want done and to meet the goals without doing as much of the work. My math is not great, for instance, and I often find solutions to hard math problems another way. And I often walk in and, like at work, I'd walk in and see, some programmer that I was friends with who was absolutely brilliant, could code circles around me and understood math and physics and things in a way that I don't. And they would be trying to solve some really hard problem. And I would just be like, why don't we just do this instead? And, a lot of times it was like, oh, crap. Okay, great. We don't have to do this work. So if you can get out of it, that's like the best. So in conclusion, anytime you use a framework or build a framework, realize that it has overhead. It's in, any of these kind of like extensible frameworks are going to add a lot of overhead. So you want to think about them as link points, and you want to reduce the amount that you use them if you need your code to go fast, right? And in the case of this example, it's Unity's update loop. But you'll find this with almost any framework. If something's going to do something hundreds and hundreds of times, try to get it out of the framework. The same thing is true of like Unity's old math library. If you called mathf.abs on something, and you pass it a float, it's going to convert that float to a double, and then it's going to pass it to C, which will then abs it, that it's going to cast it back to a double, or if maybe it does it already in double space, but it's going to pass it back to the C# framework, and then it will cast that back to a float and return you the absolute value, right? That's a ridiculous amount of framework overhead and round tripping for a very simple operation. So I'm always suspicious of frameworks, even libraries, math libraries, things like that. I want to know what they do and get a sense for them, because oftentimes getting rid of that is a big win, or at least minimizing it if you need to use it. So when you write systems, a lot of times you really just want to write exactly what you want. People get into this whole thing about extensibility and what if a customer needs to add, a new type of shape or whatever. A lot of times it never gets used. It's only used internally by the same programmer who wrote it. So, if you're going to do things like that, make sure that the binding is to something very large that won't get called 1,000 times, and make sure that you aren't just better off modifying the code. The only time you really need an extensible system is when you don't have access to the code yourself. You can, if you have full access to the code, you just go modify the code. Packing data, I often see people think about this as like memory savings, and memory savings is great, but modern consoles have like 8 gigs of RAM on them. You don't really need to save memory, but what you do need to save is bandwidth. Bandwidth of the processor dealing with this memory, bandwidth of loading and unloading this memory, and bandwidth of streaming this memory. So you really want to pack for bandwidth when anything is going to be used a lot of times in a frame. And then write your data to access memory linearly. Don't go door to door. Go door to door, not across the whole town looking for your data. And if you want to really understand that better, you can read up on some data-oriented design stuff about classes and structures, and then array of structure versus array of class. The short thing on array of structure versus array of class is you don't want really large structures of data to work with, because chances are operations might only be using a little bit of it. So sometimes you want to have a structure which has a bunch of arrays in it, so you can just grab the data that you need to access and work with it. Don't make it so that when you load that structure or class, you're loading up all kinds of stuff you're not using. You just want to work with what your transform is doing. Programming is about transforming data, right? So your transform should only load the data it needs and only work with the data it needs, and that'll make it go faster. And if you can do it all linearly and stuff. And I generally look at complex solutions for things and abstractions as a code smell. There's always times where they're useful, and abstraction and interfaces and things like that can be really wonderful for modularizing things and things like that. But they are a code smell, and you should really think about those connection points and which ones you need versus which ones are just introducing a lot of hidden performance problems. So, and that's all because CPUs are fast, memory is plentiful, but it's slow, especially if you access it out of order. And organize it, access it in order, pack it, and minimal data per transform. And always do these optimizations before you get into threading and amortization. If you just take a bunch of shit code and you run it on multiple processors, all you're doing is spreading shit around. You're not improving your code. You're not optimizing it. You're just making more bad code run on more processors. And do you really have to do the hard thing? Is it performant enough? Is there a way out of this particular thing you're trying to do? And so think about this as a design time problem, right? Of how do I make my systems so that they are performant, and not as a, hey, I've found a performance problem and now I'm going to restructure all the data in the world. Because a lot of times what I see in programs is that they're just written in a style that is fundamentally non-performing, and they don't really gain much from it. They mostly just lose. And nowadays the losses we're looking at are they're not 2x slower, they're not 5x slower, they're 1,000 times slower. So just get in the habit. I had a music teacher who told me, I was playing a piece and she yelled at me because I was just playing the piece, and she's like, what are you doing? And I'm like, I'm playing the piece for you. And she's like, nope, you're practicing mediocrity, right? She was like, you are practicing playing it without all the passion and the feeling in the notes that you need. And so you're practicing how to be mediocre. And I think when you code, you should think about the things you want that code to do, whether it's whether it's to be optimal, whether it's to generate a feel in a game, whether it's to be, you know, functionally important in whichever aspect you choose, right? Whether that's, you know, speed or code beauty or whatever your problem space you're solving is. And you should really try to get in the habit of always writing to that level of excellence. And so I don't, even when I'm scratching out basic code, I just reach for arrays. I don't reach for dictionaries unless I know it's worth the convenience. You know what I mean? And I get used to indexing things. Like every graphics programmer is just used to indexing things into arrays. And like, you know, even if you have like, instead of having a multi-dimensional array, you'll just have a single array with a little, you know, x plus y times length thing in there to basically like convert the index into the right index, a multi-array index into a single array. You know, it's just, you get in habits of these things, and then it's all easy, and everything works out and is fast. So yeah, that's the point of my talk. You know, I don't believe there's any one way to design everything. And I think that's important in all these conversations about optimizations. And before people nitpick, there's a lot of glancing over stuff in this one. The point is to give you a basic overview of how you should think about writing optimal code, and or code that can be optimized and run fast. So hope you enjoyed it. Hope it's useful. And yeah, thanks.